Yeah, and I always recommend you to access from your computer, not the smartphone or tablet, because I think our language only works on computers. In the past, we have the Android version of R. I'm not sure about iPad version, and also online version is available somewhere, but it does not have the full functionality sometimes. Yeah. Okay, so chapter 5. So last time that we studied the two tests. The one is the one sample t-test, and another is Wilcoxon signed rank test. And basically, we have just one sample of data. One sample means a set of observations. So one sample of data, and we see if the center or population mean is some specific value or the different from the specific value. Another version is our null hypothesis is the center is specific value, and the alternative is the center is larger than the sum value. And actually, another version is the smaller than, but we have the one-sided test. So anyway, so we have the two tests, the t-test and the signed rank test. T-test assume that the observations are normal. So the observation follow a normal distribution. So it's continuous and it follows normal distribution. And the signed rank test does not have any assumption, distributional assumption. Actually, the signed rank test, we have assumption that the distribution is symmetric, but often that is ignored in practice. So basically, the t-test is based on stronger assumptions. So our test result likely to reject. Our test result is likely to reject null hypothesis. So we have higher power in statistical term.
I don't think you're sharing your screen.
Yeah, I have not. Yeah.
Oh, okay.
Yeah, I will share the screen. Yes. Yeah, and on the other, yeah. So yes. So basically, if assumptions are satisfied, normal assumptions are satisfied, then it's good to use t-test because it's stronger. If not satisfied, we are forced to use different tests, such as signed rank test. And today's topic, that we have the different data. So we have two sample tests. That is very common. So we have two groups. So one group from one population and the other group from other populations. So we have two samples, one from each group. And we compare those to see if there is any difference. And we study the t-test and also the Wilcoxon version, the Wilcoxon signed rank, the Wilcoxon rank sum test, or another name is the Mann-Whitney test. So we study those. And also we study the test for variance. We have two samples and we compare the standard deviation of the one group is different from the standard deviation of the other. So that is the basically the ratio of variance. So that we consider so-called F-test to see if the two standard deviations are the same. Two variances are the same in other term. Okay, so we will share the screen and we continue chapter 5. This is actually, no. Yep. Yeah, so at first I couldn't discuss some notes on Wilcoxon signed rank test, so just I briefly cover. So Wilcoxon signed rank test still assume the continuous variables. So remember that our PhD's salary is such as, the 70,000 or 45,000, but it can take basically any value. Maybe the increment is 1 cent, but we can have any value. So that means the mathematically speaking, probability that the two people have exactly same salary, such as the 44,879.21. So this is the zero. That is our mathematical assumption. So usually when we consider continuous random variables, the probability that the two observations exactly match, that is zero. So if that assumption is violated, then we have slightly more accurate version of the test, the Wilcoxon, the exact test in exact rank test package. So often these numbers are rounded, for example, in the increment of 10,000. In such a case, we have many ties. So in such a case, the Wilcoxon.exact test is slightly more accurate than Wilcoxon test. Okay, and we have studied the two methods, the t-test and Wilcoxon signed rank test. So I want to review the overall scheme of hypothesis testing now. So I think that any test, at first we have to calculate t-statistic. So we have to calculate test statistic. Then we have to determine the distribution of test statistic. In case of t-test, the t-statistic follows t-distribution. And in case of Wilcoxon test, we have to simulate distribution based on the null hypothesis to get the distribution. But anyway, so we have to determine the distribution of test statistic under null hypothesis. Derivation is either mathematical or by simulation. And we reject H0 if the test statistic is in an extreme range in favor of H1. So basically, we calculate the p-value, right? So the p-value, then we decide. And p-value explains how extreme the test statistic is under H0. So this is the scheme. So test statistic first, then check the distribution of test statistic, then calculate p-value to see if we reject H0. Sometimes we just calculate rejection region. This is another version, but the p-value is a more general idea. So rather than constructing a rejection region, the calculating p-value is more convenient. Okay, so now the new section, the 5.3, the setting is this. So we have the two sample, one from group 1 and the other from group 2. So group 1, the sample is x1 to xn, and group 2, the sample consists of observations y1 to ym. So n and m are different. So we have different number of observations. From group 1, 100 observations, group 2, 10 observations. That's possible. For example, think about the medical experiment. We have control group, which is not given prescription, and the treatment group, that is the patient's given prescription. Usually treatment group is much smaller than control group. For example, if we consider a specific drug and find the people who did not take that drug, that is a larger population. So usually in medical experiment, one group is larger than the other. So in general, we have different sample size. Sometimes it's the same. If you can design it, usually the same sample size is better. And we have the sample mean and sample standard deviation and for each group. And our assumption is population distribution are different between group 1 and group 2. And note that the sigma x and sigma y may be different. And if these are much different, actually, they may be differentiating the sample size is more effective if you can design it. For example, if group 1 has much larger standard deviation, that means each observation is not reliable estimate for mu sub x. So in such a case, we should have a larger number of observations from group 1. So in such a case, maybe if mu x, the sigma x is much larger, maybe that we want to make n much larger than m. But yeah, if these are similar, maybe it's more effective to choose the similar number, the n and m similar. But sometimes we cannot. Okay, so in simplest case, we have sigma x is equal to sigma y. Or even if it's not equal, sometimes, okay, so we don't have any strong reason to believe that these are different. And anyway, our primary interest is mu x and mu y, the mean. So in such a case, sometimes we assume sigma x is equal to sigma y. And if sigma x is equal to sigma y, how to estimate this number? That is usually done by this. So estimate for sigma square is given by this S square. So S square is basically the weighted average of two variances. Weighted average of the sigma. So S sub x square and S sub y square. S sub x square is the sample variance for x, and S sub y square is sample variance for y. And the n is the sample size for x, and m is the sample size for y. And you can see that roughly speaking, we have n here and we have m here, and the denominator, we have n plus m. So basically, okay, so x is based on n observations. So we put the weight of n, and y has m observations. So we put the weight of m. So that is the idea. But the actually we have some adjustment, n minus 1 and m minus 1. That is a kind of natural because this is 1 over n minus 1 times summation I is equal to 1 to n xi minus x bar square. And we have n minus 1 here. So to cancel this n minus 1, it's most natural to put n minus 1 here. So actually the numerator is just a summation of all deviations, xi minus x bar or yj minus y bar. So this is the weighted average of the sample variances. So we can have this. Yeah, so if the sigma x and sigma x and sigma y are equal, that is our assumption, then we can use this test statistic T to test difference between mu x and mu y. So, sorry, then maybe I go one step ahead, but if we have two samples, x and x1 to xn and y1 to ym, this t statistic follows the t distribution with degrees of freedom n plus m minus 2. So in one sample case, the sample size is n and the distribution is t sub n minus 1. Here we have n plus m, 2 sampled, and we subtract 2. Actually, this 2 comes from the fact that we calculate x bar and y bar, and we use them instead of mu x and mu y. So we say that we lose the 2 degrees of freedom. So when we want to use mu sub x and mu sub y to calculate standard deviation, we substitute these numbers by x bar and y bar, and that technical difference that makes this minus 2. So we don't prove this, but it's complicated linear algebra. And yeah, so this t statistic follows t distribution. So what is this statistic? This is x bar minus y bar. So basically this is different between, so this is an indicator for the difference between mu x minus mu y. So it's a kind of similar quantity to this. And the numerator is actually yeah, so the variance of x bar minus y bar, basically. Yeah, so we have the x bar. So the variance of x bar is equal to s squared over n, and the variance of y bar is S square over M. Right? So variance of X bar minus Y bar. Our assumption is that these observations are independent. So if these X and Y are independent, then this is actually the variance of X bar plus variance of Y bar. So that is equal to actually the S square over N plus S square over M. So to calculate standard deviation, we take square root. So standard deviation of X bar minus Y bar, this is actually the square root of this. So this is S times square root of 1 minus N over plus 1 over M. So actually this comes from, this one comes from this reason. So basically the X bar minus Y bar divided by standard deviation of X bar minus Y bar, that is the T statistic. So this is actually standard deviation of X bar minus Y bar. So if X's are and Xi's and Yj's are independent and the sigma X and the sigma Y are equal, this T statistic follows the T distribution. So the test procedure uses this statistic as test statistic. So T represents basically the difference between mu X and mu Y, and also it's adjusted by the size of variability. So this ratio, capital T, is a good indicator for difference between mu X minus mu Y. So if H0 is this and H1 is mu X is not equal to mu Y, basically, if absolute value of T is large enough, we reject H0 because this is an indication that mu X and mu Y are different. Any questions? So we have different test quantity. I think I got one question, maybe. Why is having the, I got a question. Why is having the same sample size better? Is it easier to do calculation or any calculation more accurate? It's more accurate. So, you know, if you want to get information on two populations, then if one is very accurate but one is very inaccurate, the accuracy for the first one is ruined when we compare two. Right. So basically, we want to get two numbers at the same accuracy level. So that is our idea. Yeah. So if sigma X and sigma Y are the same, then the same sample size, maximize our resource to know the truth. Yeah. So often the two levels should be the same, right? So if you have you have two doors in your house, and if one door has the five locks and one door has one lock, then probably that is not efficient way to use 6 locks. Yeah. Okay. And here is one concrete example. So we have this data for average math test scores for 5th graders in 7 Detroit schools and 5 Dearborn schools. Actually, this is the real data. And test if the two groups have significant difference with a significance level at 5% level, with significance level at 5%. So we have the 7 scores. Actually, each score is average of many students. I took this data because average of many scores is distributed normal in most cases. Under very mild condition, that's true. And we have 7 numbers here. Actually, it ranges from 493.1 to 529.1. And the Dearborn School, we have 5 observations. Everything is actually larger than 507, and the largest one is for 530. It looks like the Detroit has lower score. For example, these 5 schools have lower than even lowest score in Dearborn. So my guess is probably the Dearborn has significantly higher score, but we want to statistically verify it. And actually, there are many schools in the Detroit and Dearborn, so we just picked up randomly the 7 schools and 5 schools. And we use the t-dot test function. This is the same as one sample t-test, but the difference is we have 2 inputs, the one vector dt and the other vector db. And we have to specify the variance dot equal is equal to true. So the default is the variance dot equal is false. So because we have no reason to believe that the variances are equal. But we are thinking about simplest case, so this. And then we have degrees of freedom 10. Remember that we have 7 observations in Detroit, 5 observations in Dearborn. So 7 plus 5 minus 2 is 10. Then the t-value is negative 2.07. We put the Detroit first. So basically the x bar, this is Detroit, and the y bar, Dearborn. So this is negative 2.07. So actually Detroit has lower score. And p-value 0.064. This is two-sided test in default. So that means if we have t-distribution and we have negative 2.07, then this area plus this area, the total area sum up to 0.06477. And this is actually larger than 0.05. So it's marginal. It's almost close to 0.5. But at 5% significance level, we cannot say the Detroit is significantly different score from Dearborn. Maybe if we increase the sample size, maybe this difference is more significant. In a common sense, the statistical tests are pretty conservative. So 95% confidence interval, or I mean the 5% rejection region, that is pretty conservative. Yeah. In real life, usually if we have the 2 observations and the 2 observations have similar tendency, then that we conclude something, right? So once I had the 2 earbuds, I mean 2 pairs of earbuds, and in both earbuds, then actually the right-hand side is broken. And I tested those 2 with my computer, and I believe that the computer has some problem because on both pairs of earbuds, then right-hand side does not work. And it took time to identify the reason. But just 2 observations, maybe statistically not significant. So it's different. And the statistical tests are usually very conservative in common sense. Yeah, of course, we can calculate everything from scratch. We have formula, so we can calculate t-statistic and p-value, df, by ourselves. And the confidence interval is also given. Confidence interval is negative 29 to positive 1.05. So this is basically the estimate for mu x minus mu y. X is for Detroit, and this is Dearborn. So the true mean score, if we survey all the population, all schools in Detroit and Dearborn, the mu x minus mu y is in this range. So that means the Detroit mean score, population mean score, may be up to negative 29 points. So the 29 point lower than Dearborn, but possibly 1 point higher than Dearborn. So range is negative 29 to positive 1. And actually it includes 0. So that means the mu x is equal to mu y is not rejected. So that is our conclusion. So this is 95% confidence interval, and it corresponds to null hypothesis of mu x is equal to mu y. So if this includes 0, we reject null hypothesis. It does not include 0, we reject null hypothesis. And this is sample mean, 506 and 520. So difference is about 14. So estimate is 14, but the range is negative 29 to positive 1. So that is the conclusion. Yep. And we can calculate everything from scratch by using formulas. if we would like. Do you have any questions so far? I think I got one question. Can't we infer from experience that the earbuds aren't that likely to be broken? So another one being broken in Sri Lanka. Yes, yeah, that's possible. Yeah. It may be affected by the probability of the earbuds broken. But the both are actually, I got both ones in the airplane. So it's a very cheap one. Maybe it costs less than $2 or something. So actually it breaks pretty often. Yes, the confidence interval, why 95%? Yeah, actually we have option. We can add option, the conf dot int. I think probably that maybe confidence level. Maybe we can check it in our language. Help t.test. We have the conf.level function, conf.level function, and the default value is equal to 0.95. So just this default value is used to calculate confidence interval. So if we want to calculate, for example, 90% confidence interval, then you can specify this is equal to 0.90, then we get the 95% confidence interval here. Yeah. Okay, many good questions. And okay, so now we go on to the next. Yeah, and the next case is the sigma x is not equal to sigma y. That is the usual case. So to population have different variability. I don't know, the male height and female height have different standard deviation. I don't really know, but the sometimes two groups have certainly different the variations. Maybe the temperature in rainy days and temperature in sunny days. I think obviously in at least Midwest in winter, the sunny days, the variation is much higher. Yeah, so in such a case, we have some adjustment. Okay, so last time this was s square over n and s square over m. But this time, just we have two different estimate. So standard, the variance of x and variance of y here. Yeah, so actually the sigma x is equal to sigma y. Previous case, I write this as this, but this is actually equal to this as mentioned. So just we replace this s, this s and this s by sx square and sy square. So almost the same quantity. But this actually makes this degrees of freedom different. And degrees of freedom is actually, okay, so actually this does not really follow t-distribution. This does not follow this t-distribution, but approximately this follows t-distribution with degrees of freedom k. And k is calculated as this quantity. Okay. Okay, so this is so complicated, and it is based on some asymptotic result in statistics. But sorry, this is some Taylor approximation in statistical theory. But the idea is that degrees of freedom is affected by the relative importance of relative size of sx square and s sub y square. So if, you know, sx square is very similar to sy square, so this is the previous case, the same as previous case. So in this case, the k, in this case, the k is approximately equal to n plus m minus 2. But suppose that the s sub x square is much larger than s sub y square, then in this case, k is actually approximately n minus 1. Why? Because the y does not have any variability, almost no variability compared to x. So only the variability of x matters for the test. And x has n observations, so degrees of freedom is n minus 1. And if s sub x is much less than s sub y square, and k is approximately m minus 1. And if in between, like S sub x squared is twice as large as Si squared, so in such a case, the somewhere in between. So the K, the formula for K, that represents that situation. So it depends on S sub x squared and S sub y squared, but also depends on N and M. So you don't have to remember this formula, but yeah, so we have some approximation theory. And this test statistic, so we can construct t-test based on this statistic, and that is called Welch's t-test. And this is the most popular test for two-sample test. We have less assumption, sigma x may be different from sigma y. And if you calculate this k, actually this becomes fractional. Suppose n is equal to 7 and m is equal to 5, and this number may be 9.5 or something like that, or even 9.14 or something. So, but the t distribution is defined by random variables using this. So suppose that x1 and xk are standard normal, independent standard normal random variable, and z is also independent, the normal random variable standard. Then we define the t random variable by this. But this k, of course, should be an integer. Otherwise, we cannot define this. If k is 1.5, how to define this? But actually, if you calculate the PDF of this function, PDF is the probability density function, so like this shape, and this equation, say this as f sub k of t. So this is actually expressed as this equation. So originally k was an integer, but we can calculate the gamma function is continuous function. It uses the integration of the some exponential function. But the gamma is a continuous function, and actually the f sub k of x is written as this one, and this can be generalized into fractional k. So k is any number, such as 9.4 or 9.19 or whatever. Yeah, of course, k should be positive at least positive. I think it should be at least larger than or equal to 1, but any number, any continuous number k, the real number k, that we can define f sub k of x as long as k is larger than, I think larger than 1, larger than or equal to 1. Yeah, so in this way, the t distribution with fractional k is, fractional degrees of freedom is well defined. Yeah. How about complex k? So yeah, actually the most statistical theory does not even think about the complex value. So, when you see maybe pretty advanced PhD level statistics book, still definition of random variable is the the probability space to real numbers. So I think the complex, the very few people consider it. Maybe you can search for the context, but usually people don't think about it. So that means I think the complex, the degrees of freedom is even beyond that level. So I think no theory for that. Okay, and the t-test, Welch's t-test. Actually, this is the default method in R. So you can just use t.test, then put the two samples. Then we get the t statistic, negative 2.2462, slightly different because we distinguish sample variance for x and y. And the degrees of freedom was 10 originally, but here 9.917, not much different from 10. So that is indication that the two standard deviations are similar. Yeah, but the p-value, interestingly, it becomes slightly smaller it sometimes becomes larger than equal variance case, sometimes gets smaller, but actually this is less than 0.05. So our conclusion is a little different. So it's hard to decide, but the Welch's t-test has basically, the less assumption. So as a tendency, it's hard to reject null hypothesis. And even with Welch's test, we reject null hypothesis. So I think it's pretty fair to say that we can reject H naught. And confidence interval, -28 to -0.09. So it does not include 0 this time. So we can say that we can 28.3 to -0.09. So this does not include 0. So we can say that the two difference, the mu x minus mu y, is always negative. So I mean, with 95% confidence, that we can say mu x mu y, mu x minus mu y is negative. So null hypothesis of mu x is equal to mu y is rejected. Yeah. Any questions so far? Okay. And yeah. And that's the two sample t-test. And the next topic is the comparison of two variances. So in our context, we can test the variance in Detroit and variance in Dearborn. So we can test this. So one natural use is, to decide the t-test assumption, whether we should use Welch's t-test or equal variance t-test. But this is often used to compare two models. So think about the error size of model 1 is the sigma x, and the error size for model 2 is sigma y. So x is some error of model 1, errors of model 1. And y is the errors of model 2 or something like that. Then the variance of sigma y and variance of variance of x and variance of y. So this is a kind of model accuracy. And often we want to compare the two model accuracies. So this test is often used to compare the two different models of two different statistical models. Null hypothesis is sigma x is equal to sigma y square, and alternative is not. The one-sided test is also possible, but so far we ignore it. And the test statistic, naturally that we take just the ratio of these two. Maybe the difference is also considered. But anyway, so these two quantities are both positive. And actually, mathematically, the distribution of this ratio is easier to derive. Easier, I mean, the distribution of this ratio is more mathematically beautiful distribution. So that's why we take the ratio. And this actually follows the F distribution with df n-1 and m-1. So actually the F distribution applies. And yes, n is sample size for x and m is sample size for y. And based on this test statistic, we can construct a test. So we have F distribution. F distribution is like this, usually skewed distribution. And the alternative hypothesis is sigma x square is not equal to sigma y square. If sigma x is much smaller, F ratio, F statistic is small, like the falls in this range, right? And if F statistic is, the sigma x is much larger, then F statistic falls in this range or something like that. So if our test statistic falls in this extreme range, then this is an indication of sigma x is not equal to sigma y. So this is the rejection region. So actually, if we observe the F statistic F, then this is the p-value. If p-value is less than 0.05, the lowercase f is extreme enough to reject null hypothesis. So that is the rejection region. So this is two-sided test, but the one-sided test, as usual, that we only reject the only one side of this distribution. So one-sided test, p-value is only one side. So it's just the half size of the two-sided test. Yeah, so always we have two-sided test and one-sided test, but that variation is very similar to t-test, the one sample t-test. So you can see how we can construct the one-sided test and the two-sided test. And this is code, so variance.test. Yeah, to compare two models, sometimes we have different functions. The R have some ANOVA function to compare two models. But if you simply compare the variances of two vectors, then this variance.test, a var.test function that works. And the variance test of dt and dv, so we have two inputs, two vectors, and default is two-sided test. And F test is done here, and F statistic is 2.54. So F test, the F statistic is around 1. So F is around 1. So that is maybe one good thing to say if H naught is true. So H naught means the sigma x square is equal to sigma y square, right? So in this case, F is okay. F is sx square over s sub y square. So if null hypothesis is true, then F is around 1, around 1. So 2.54 is somewhat large, but we don't exactly know the exact. We don't exactly know the distribution of F, so we cannot say at this point, but we can say it's slightly different. Sigma x square is about 2.5 times larger than sigma y square. Or if you just compare sigma x and sigma y, maybe 1.6 times larger. It's slightly larger. Maybe difference is significant. That is our conclusion. But when we calculate the p-value from this test, actually, that p-value is 0.38, much larger than 0.05. So statistically, that we cannot reject null hypothesis. This is the sample size -1 for numerator, and this is sample size -1 for denominator. We have 7 schools in Detroit, 5 schools in Dearborn. And yeah, so intuitively, the difference of 2.45 times. This is a little large number and significantly different from 1. But usually it's hard to reject the null hypothesis in this case, because this is the variance. The variance is squared quantity. So think about the definition of the sample variance. If just one outlier is there, for example, x1 is much larger than x bar, this number gets very large. So it's affected by, outliers, extreme values, extreme observations. So with 7 observations and 5 observations, it's very hard to reject null hypothesis. So statistical testing is pretty conservative, especially this kind of, the test for variance. Yeah, so ratio of variance is 2.54. And actually the 95%, this is not confidence interval, but the confidence interval is here. So sigma x square over sigma y square will be between 0.27 and 15.8. So 0.27, just the difference is maybe 3.5 times, but the 15.83 difference is almost 16 times. So this tends to be larger than 1, probably, but it's not significant because it includes 1. So sigma x square over sigma y square is in this range. 0.27 is in some sense close to 1 because it's only the the ratio is only just the 3.5. So 1 over 0.27 is around 3.5. So yeah, difference is not that large compared to 15.8, but still we cannot reject H naught. And the threshold values for rejection is 0.16 to 9.19. So if F statistic, this is F statistic, if F was larger than 9.19, then reject H naught. Or if F is smaller than 0.16, then we reject H naught. Yeah, and our test statistic, the p-value is much larger than 0.05. Yep. Any questions? So in chapter 5, this section is slightly different because this is test for variance. And other tests are all about the population mean. The one sample test, two sample tests, and also we study paired test, but it's similar. Okay, so the next one, two sample Wilcoxon test. So we have, okay, so one sample and the two sample and the normal case and non-normal case. And we have the one sample t-test, two sample t-test, there are also Welch's t-test, and the Wilcoxon signed rank test. And then now that we study Wilcoxon two sample test. So that is called Wilcoxon rank sum test or Mann-Whitney test. So we are studying here. And our assumption is we have two samples and all random variables are independent. Xi's are from the same population. So these are IID, the same distribution, follows the same distribution. Yj's are also identical, the same distribution. And observations are ordinal. So X and Y are usually continuous random variables, but even it do not have to be continuous, maybe rating that is possible. And under null hypothesis, Xi's and Yj's have the same distribution. So we don't know what distribution X follows, maybe skewed distribution. And then Y also has the same distribution. And alternative is Xi's and Yj's have different distributions. Maybe X has this distribution, Y has this distribution, or something like that. So it's more general, much more general than even Wilcoxon signed rank test. Almost no assumptions on distributions. And to do one-sided test, the alternative hypothesis is either X is larger than Y as a tendency, or X is smaller than Y as a tendency. So it's a vague, but the two-sided test alternative is simple. The Xi's and Yj's are just different. But the one-sided test, we have to define some direction. So how different? But this distribution may not even have mean. So we can only say alternative hypothesis is X is larger than Y as tendency. So even population means may not exist, but often we describe this alternative as mu X is larger than mu Y or mu X is smaller than mu Y. But I think these descriptions are not really accurate mathematically, but conventionally we use these expressions as alternative hypothesis. Okay, so maybe we consider this from an example. Oh, sorry about, yeah, we don't really have the exactly we want. Yeah, so the idea is we order numbers. Okay, maybe I should, sorry, I think I should have some page to explain that. Oh yeah, we have, sorry, yeah, we have it. Yeah. So we have the 7 observations from Detroit, and we have 5 observations from Dearborn. Then at first, we just make this as one group, and we rank observations. So you can see the smallest one is this one. And the second smallest one, maybe this one, and the third, and the fourth, and the fifth, and the sixth, and what's seventh? The seventh here, maybe. And the eighth here, and the ninth, 10th, 11th, and 12th. And we have these ranks we have. Then we consider the total rank of these 7, the Detroit schools, and these 5, the Dearborn schools. Then even distribution is unknown, that we can say, we can tell the which district has a lower score or higher score. You can see if we see ranks, most the low ranks are in Detroit. 1, 2, 3, 4, 5 is in Detroit, and the other is 8 and 11. But the Dearborn, we have 6, 7, 9, 10, 12, so it's much larger. So using this information that we can test. Of course, we lost a lot of information that we have concrete numbers, but we lost those information. But even we lost those information still based on rank, then we can test. And we have less assumption on distribution of these 2 districts. And if we calculate the rank for Detroit, that is actually what? The 8 plus 2 plus 4 plus 3 plus 1 plus 5 plus 11. So that is 10, 18, 34, right? And this is kind of the useful statistic. But the 7 schools, we have 7 schools. So at least the sum of ranks is equal to 1 plus 2 plus up to 7. So that is the 7 times 8 divided by 2, so 28. So as a test statistic, we use 34 minus 28. So that is 6. So that is our important information. And we do the same for Dearborn School. So Dearborn School, that we have these 5 observations, and this totals 44, I think. But the 5 schools, at least that we have 1 plus 2 plus 3 plus 4 plus 5. So this is 15. So 44 minus 15 is 29. So we use this 29 as useful, summarize the information. And basically we reject H0 if this number 6 is too small, or this number 29 is too small. So that is our testing scheme. Yeah. And actually we calculate the, actually this is the 2-sided test. So the conventionally, we use the, 2-sided. So we basically calculate the p-value as the 2 times probability of this test statistic. This test statistic, we say W, maybe this one as W asterisk. The W is less than or equal to 6, and we have 2-sided test. So we multiply this by 2. Yes, and actually this is equal to, I'm not sure, but yeah, conventionally we use this as p-value for 2-sided test. So this is the 0.07323. So we do not reject null hypothesis. So that is the our Wilcoxon rank sum test. And the theory behind it is here. So we have observed Xi's and Yj's, then we calculate the total rank of observations in X and observations in Y. And we subtract the minimum possible rank sum for each group. Then that number, W and W asterisk, are a good test statistic. And based on these, that we test the hypothesis. And for two-sided test, that we reject null hypothesis if the W is, sorry. So we have to define p-values to decide whether or not we reject H0. And suppose that the W lowercase is the test statistic from our sample, and we calculate the probability of more extreme event than this lowercase w. And then we multiply by 2. That is the two-sided the p-value. And if we have one-sided test, the mu x is less than mu y, then the p-value is just a half of this p of this random variable is less than w. Lowercase w is our realization, our test stat. The test statistic based on our sample. And this is random variable. Okay. So in general, what's the distribution of, what's the random variable W? And the more extreme event than our test statistic happens with only this probability. And the two-sided test for the other alternative, the p-value is this. Yeah, so based on these p-values, that we either reject or accept null hypothesis. So for example, for two-sided test, that if so if maybe we can skip this. The rejection region isn't really necessary. So as long as we can calculate p-value, that we can decide. So so we can say the p-value is less than 0.05, we reject null hypothesis. And also that we can construct rejection region based on this theory. So basically, we consider the distribution of W, and basically we set the W alpha over 2. So this is the quantile points, and if the test statistic falls in this range, then actually this corresponds to this range. So sorry. We usually think about the smaller the test statistic of these two. So we have calculated W and W star value, and that we take the smaller of W and W asterisk. Then if this is less than the threshold, the W sub alpha over 2, then we reject the null hypothesis. And one-sided test, that we can also construct rejection region in similar way. And in our code, we can use Wilcox.test function to get these numbers, the W and P value. Actually the W and the W asterisk is a kind of the dual quantity, because the W plus W asterisk is always constant, right? Because we have in total 12 observations. So total rank, the sum of all ranks is equal to, summation of 1 to 12. Okay, so it's constant. So W plus W asterisk is constant. So usually the R only reports the statistic W. And this is actually the two-sided Wilcoxon test result. That's the Wilcoxon rank sum test result. But if we want to get the one-sided, we can specify alternative in this way. And this p-values and also some threshold for rejection region can be calculated by simulation. So we don't have a beautiful theory behind it. Okay, so now that we do exercise, exercise 6, we are going to do. I don't know if exercise 6 is here. Okay, not here. So we don't have much time, but yeah, here is exercise 6. So we do a t-test and the confidence interval. So we have the weight. So we have the newborn babies, and we have null hypothesis, and alternative is the just mu is not equal to 4.0, and we can do t-test. But the also that we can do calculation of confidence interval and so on. Okay, so I will set up the breakout rooms to do it. And the question 1 maybe we can do.